Hello and welcome to this clip going through a level question, this time using boiling point data alone to sort out and identify a set of organic compounds. So like with any level question, it's always a good idea to make a plan of some kind. And what I do is possibly draw out the skeletal formulae or displayed formulae. It might be helpful to try and deduce some of the likely intermolecular forces that are at work. So the next thing to consider is obviously what kind of things in the molecule might affect the intermolecular forces that might arise. So if you think back to the first year, we're looking at things like branching, polar bonds, permanent dipoles maybe, or hydrogen bonding. So what I'd do is I'd think about all the intermolecular forces that I've got to play with. I've got London forces, I've got permanent dipole-dipole interactions, and I've also got hydrogen bonding. So if you remember that London forces take place in all covalent compounds, and that permanent dipole-dipole interactions need polar bonds with a permanent dipole present, but London forces plus hydrogen bonding mean you have to have hydrogen bonded to nitrogen, oxygen, or fluorine. So the two compounds that will have London forces only are butane and 2-methylpropane or methylpropane. So London forces are the weakest intermolecular force, so they need the least energy to overcome. So between these two candidates, the branched compound is going to have less surface contact points, so that's going to have the lowest boiling point out of the two. So now we can pick the two lowest boiling points in the table, and allows us to identify C as CH3, CH2, CH3, and B as CH3, CH3, CH3. Okay, so now moving on to the category where you've got London forces plus permanent dipole-dipole interactions. With this one, we have a candidate in chloropropane. The carbon-chlorine bond has a permanent dipole, which allows us to identify the middle boiling point of 35 degrees C as belonging to compound D. So if we look at the two compounds that have hydrogen bonding, there's not a lot between them. They have the same number of carbons in their carbon chain and no branching, so that means no difference in the London forces from that part of the molecule. However, the functional groups are different, and both functional groups obviously have an electronegative atom that's bonded to hydrogen. In one case you've got nitrogen, in the other case you've got oxygen. So how do you tell the difference between these two, or predict the difference in boiling point? Well, if you remember, a hydrogen bond needs a lone pair, and the more lone pairs on the same electronegative atom bonded to hydrogen, the more potential hydrogen bonds you could have. So if you consider that oxygen has 2 spare lone pairs, and nitrogen has only 1, therefore only 1 hydrogen bond can take place in nitrogen, and 2 hydrogen bonds can take place to oxygen. So therefore that means that the alcohol has the highest boiling point of the lot, and the second highest boiling point is the amine. So that allows us to slot those final two into place. So hopefully you found this a fairly straightforward question. Once you've dialed into the link between intermolecular forces and boiling point and structure, it should have sort of fallen into place quite easily. So until next time, thanks for listening and see you soon.